Okay, let's dive into this. We're going to talk about just one tiny keyword in Swift, but don't let its size fool you. It's kind of magical. It's the key that lets us build these incredibly complex, self-referencing data structures like trees or math formulas and do it with surprising elegance.
So it all kicks off with this, well, it's a puzzle that feels like a total paradox, right? How can a data type possibly contain a value of itself? Think about it like a Russian nesting doll, but every doll inside is identical. If a box contains an identical box, which contains another identical box, how on earth could you ever figure out its total size? This is the core problem we're about to solve.
And the feature that throws us right into this puzzle is what's called a recursive enum. In plain English, it's just an enum, or one or more of its cases holds another instance of that very same enum. It's a data type that's literally defined in terms of itself. Kind of mind-bending, right?
So you might be asking, why would I even want to do this? Well, it turns out a ton of the data structures we deal with every day are naturally nested. You can see it right here. We're talking about things like mathematical expressions, where you have an addition of two other expressions, or linked lists, JSON data, tree structures, even nested UI components. They all have this self-referential thing going on, and recursive enums are just a beautifully clean way to model them in code.
But of course, there's a catch, a big one. The Swift compiler, when it's trying to build your app, just hits a wall with these recursive types. It sees this, and it has a complete meltdown. See, here's the fundamental rule. Before your app ever runs, Swift absolutely must know the exact amount of memory to set aside for every single value. It has to know the size of an int, a string, and any custom type you create. There are no exceptions to this rule.
And that's where everything just falls apart. If an enum case contains the enum itself, the compiler gets trapped. To know the size of the enum, it has to know the size of its case, which contains the enum, whose size it needs to know, and on it goes. Forever. The compiler just throws its hands up. It can't do it.
So, how do we get out of this infinite loop? Well, Swift gives us this one simple, super elegant keyword that just solves the whole thing. And that keyword is indirect. Okay, so what indirect is really doing is giving a special instruction to the compiler. Instead of trying to cram the entire nested value right inside, which is what causes that infinite size problem, it tells the compiler, hey, just store a reference to the value's location in memory. It's like putting a little note inside that says the real box is over there. And that reference, or pointer, has a fixed predictable size. Suddenly, the compiler knows exactly how much memory it needs, the infinite loop is broken, and our problem is solved. It's brilliant.
All right, theory's great, but let's see how this actually looks in your code, because you've got a couple of really flexible ways to use it, depending on exactly what you're building.
And you have some fantastic flexibility here. Check this out. On the left, we've got this expression enum for math. Now, look closely. The number case, not recursive, but the addition case, totally recursive. It holds two other expressions. So we're being really precise here, just adding indirect to the one case that needs it. But then on the right, you've got a linked list. By its very nature, every single node has to point to the next part of the list, so it just makes sense to mark the entire enum as indirect right from the start. It's all about choosing the right tool for the job.
Okay, so we've walked through the problem, this kind of mind-bending paradox, and the super clean solution. Let's just wrap it up and talk about the big takeaways here and why this tiny keyword is actually a huge deal for writing great Swift code.
So here's what you really need to remember. First up, recursive enums, they're your go-to for modeling these complex nested data structures. Second, indirect is the magic word that makes it all possible. Third, it works by telling the compiler to use a pointer, which has a fixed size and breaks that infinite loop. And finally, you've got the choice. You can put it on just one case or on the whole enum.
And hey, one last really important thing to keep in your back pocket. This whole recursive superpower is only for enums with associated values, the kind that can carry extra data. Your regular old enums with raw values like case north equals 1, they just represent fixed constants. They don't have anywhere to put a nested value, so this whole thing doesn't even apply to them. This power is all for those enums with associated values.
And that's really the whole story. It's pretty amazing how one little keyword unlocks so much power, letting you model some seriously complex stuff way more elegantly than in a lot of other languages. So the only question left is, now that you've got the key, what kind of cool, complex structures are you going to build?